quiet archive record. Tonight, we're stepping into a slow unfolding. Settle in, let the outside world dissolve, and gently descend into tonight's world. The Fermi paradox is a simple question that opens into a wide, uneasy silence. The universe looks old, vast, and full of places where life could exist. Our galaxy alone holds hundreds of billions of stars. Many of them are older than the sun. If life can start in more than one place, then over cosmic time it could have had many chances to spread, to build machines, to send signals, to leave traces. And yet, when we listen, we do not hear a clear answer. We do not see obvious visitors or obvious engineering on a galactic scale. Tonight, we treat the paradox like a map of possibilities. We move through practical limits, biological bottlenecks, social choices, and dark outcomes that people usually avoid saying out loud. Each idea is a possible answer, not a final truth. Some answers can be tested. Others are warnings about our own future. Tonight, we go through 75 possible answers to the Fermi paradox. The paradox begins with a mismatch between numbers and experience. The numbers come from the scale of the galaxy and the time available. If even a small fraction of stars host planets, and even a smaller fraction of those planets develop life, and even a smaller fraction develop intelligence, there could still be many civilizations. If any of those civilizations build radio, lasers, probes, or large space industry, we might expect detectable signals or visible structures. The experience so far is quiet. That quiet can mean many things. It can mean we have not looked well enough or in the right way. It can mean the signals are too weak or too brief. It can mean intelligent life is rare. It can mean intelligent life is common, but chooses not to speak. It can mean civilizations end before they expand. It can mean we are early. It can mean we are late. To keep this grounded, it helps to separate three questions. First, how often does life begin? Second, how often does life become complex and intelligent? Third, how long does intelligence last in a way that leaves detectable traces? The paradox appears when you assume the first two happen fairly often, and the third lasts long enough for expansion or communication. If one of these steps is far harder than we think, the quiet makes sense. 1. Life is extremely rare. One answer is that the simplest step, the origin of life, is a near miracle. Chemistry can build many organic molecules, but turning that chemistry into a self-sustaining system that replicates with variation might be far less likely than we hope. If the odds are tiny, then even a galaxy full of planets can still be mostly sterile. 2. We do not understand how life began. A related answer is that our ignorance is doing the work. We have one example. We do not have a proven path from non-life to life. Without that, we cannot safely estimate how common it is. The quiet might simply be the correct default when you only have one data point. 3. Earth had a lucky sequence of events. Life may need a long chain of favorable conditions that almost never line up. The right planet size, the right chemicals, the right energy sources, the right stability, and the right timing might have to occur in a particular order. If the chain has many links, the final probability collapses. 4. The right kind of star is uncommon in practice. Many stars are unstable, flare often, or change in ways that harm early life. Even if planets are common, planets around quiet, long-lived stars with stable light might be rarer than the simple star count suggests. 5. Planets need plate tectonics. Some scientists argue that plate tectonics helps regulate climate over long periods by recycling carbon and other elements. Without it, a planet might swing into extreme greenhouse or deep freeze and stay there. If tectonics is rare, stable habitable worlds may be rare. 6. Planets need a magnetic field. A strong magnetic field can help protect an atmosphere from being stripped by stellar wind. If many planets lose their air early, they may never hold surface water long enough for life to gain a foothold. 7. Planets need a large moon. A large moon can stabilize a planet's tilt and, by extension, its seasons and climate. It can also drive tides, which may have helped early chemistry. If large moons are unusual, Earth-like long-term stability might be uncommon. 8. Planets need the right amount of water. Too little water and chemistry may not have enough liquid medium. Too much water and a planet becomes a global ocean with less land, less weathering, and maybe fewer nutrient cycles. Earth might sit in a narrow middle range. 9. Planets need continents. Land can create diverse environments and cycles that might speed complexity. If most habitable planets are water worlds without continents, life might exist but remain simple for longer. 10. Planets need the right mix of elements. Life uses more than carbon and water. It needs phosphorus, sulfur, iron, and a range of trace metals. The availability of these elements depends on a planet's formation and history. Many planets may be poor in crucial nutrients. 11. The early Earth had the right energy gradients. Life needs usable energy differences, like hot and cold, acidic and basic, or chemical fuel and oxidizer. Hydrothermal vents, lightning, and sunlight all provide gradients. Maybe Earth had an unusual balance that allowed life to start. 12. The first cells are a huge barrier. Even if basic replicators are possible, building a cell with a boundary, internal chemistry, and reliable replication may be extremely hard. The step from chemistry to the first true cell may be the great filter. 13. The jump to complex cells is rare. On Earth, complex cells with nuclei, called eukaryotes, appeared long after simple cells. That event may have required a rare merger between organisms, like a symbiosis that became permanent. If that merger is rare, many worlds may stay microbial. 14. Multicellular life is rare. Complex multicellular life also took a long time on Earth. It may require oxygen levels, genetic toolkits, and stable environments that are not common. 15. Intelligence is rare. Even with complex life, intelligence that builds technology might be uncommon. Earth had many animals for hundreds of millions of years, but only one species developed radio. Intelligence may not be an inevitable outcome. 16. Tool-making intelligence is rare. Some animals are smart, but they lack hands, fire control, or the social structures for cumulative technology. A planet might have dolphins, crows, or octopus-like minds, but no easy path to build antennas. 17. Language-like communication is rare. Advanced technology depends on teaching and sharing knowledge across generations. If a species has limited communication, it may never build complex society. 18. Fire is rare. Fire may be essential for early industrial development. If a planet's environment does not allow controlled fire, or if oxygen levels are too low, a species might remain pre-industrial forever. 19. Land is necessary for early industry. Industry may be much harder underwater. A civilization in an ocean world might reach intelligence but have no metallurgy, no electricity, and no spaceflight. at least not in a way we recognize. 20. The window for technology is short. Even if intelligence arises, it may have only a brief time when it uses loud, easily detected technologies. Radio leakage might last a century before switching to tighter communication. If that window is short, we may miss most civilizations. 21. Civilizations self-destruct quickly. A common answer is that technological civilizations tend to end themselves soon after reaching power. Nuclear war, engineered disease, runaway AI, or ecological collapse could wipe them out before they spread. 22. Civilizations stagnate. Instead of self-destruction, many civilizations might reach a stable level and stop innovating. They might solve basic needs and then prefer art, virtual worlds, or spiritual focus over expansion. 23. Space is too hard. Interstellar travel may be far more difficult than popular fiction suggests. Even if it is possible, it may be so expensive that few civilizations attempt it. 24. The speed of light is a hard limit. If you cannot go faster than light, then building a galaxy-spanning culture is slow and fragile. Over long times, colonies drift apart and lose coordination. That may reduce the motivation to expand. 25. Interstellar colonization is not inevitable. A civilization might have no interest in sending people to other stars. It might see it as pointless, risky, or morally wrong. 26. They stay at home and build inward. A civilization might focus on maximizing life quality in its home system. With enough energy, a single system can support enormous populations using habitats and efficient recycling. 27. They live in simulations. If advanced computing allows rich virtual realities, many beings may choose to live in digital worlds. Their outward footprint could be minimal, and their signals could be tightly controlled. 28. They communicate in ways we do not detect. We mostly search for radio and simple laser pulses. Others might use neutrinos, gravitational waves, tight beam lasers aimed only at known targets, or communication embedded in physical probes. 29. Our search methods are immature. We have searched only a tiny fraction of the relevant space of frequencies, times, directions, and signal types. The quiet may simply reflect how early the search is. 30. Signals are brief and rare. Even if civilizations transmit, they may do it only occasionally. A beacon might fire once per week or once per year. If we do not watch long enough, we miss it. 31. Signals are disguised as noise. Advanced communication can look like random noise to outsiders, because good encryption and compression remove patterns. A signal could be present in our data and still appear meaningless. 32. We assume the wrong timescale. Civilizations may rise and fall over millions of years. If the average lifetime of a detectable civilization is, say, 10,000 years, that is still a blink in the age of the galaxy. 33. We are early. The galaxy may be in a phase where intelligent life is only now becoming common. Many stars older than the Sun may have had too many hazards in the past, like frequent supernovae or gamma-ray bursts. 34. We are late. The opposite possibility is that the best time for life was earlier, and we are arriving after others have already come and gone. The traces might be subtle or erased. 35. The galaxy is dangerous. High-energy events can sterilize large regions. If such events are common enough, they can reset biological progress repeatedly, preventing long-lived civilizations. 36. Gamma-ray bursts reset planets. Gamma-ray bursts are rare but powerful. A close burst could destroy ozone and cause mass extinctions. If bursts are common in the past, they could keep planets from reaching intelligence for long periods. 37. Supernovae and cosmic rays. Nearby supernovae can increase radiation and change climate. Repeated exposure could slow evolution or push species toward underground or underwater niches, limiting technology. 38. Frequent asteroid impacts. If many habitable planets experience frequent large impacts, complex life may be repeatedly wiped out before intelligence emerges. 39. Runaway greenhouse is common. Many worlds may become like Venus. A slight increase in heat can evaporate oceans and trap more heat, making the planet permanently hostile. 40. Snowball worlds are common. Some planets may freeze over and stay frozen. Life might survive under ice, but complex land life and technology become unlikely. 41. The oxygen trap. Too little oxygen limits energy for large animals. Too much oxygen makes wildfires more likely. Earth had a narrow path where oxygen rose enough for complexity without constant global fires. 42. Evolution is not goal-driven. Many people assume evolution pushes toward intelligence. It does not. It pushes toward survival in local niches. Intelligence is just one tool, and it may not be favored often. 43. The intelligence trap. Even when intelligence arises, it can lead to overconfidence, risky behavior, and short-term thinking. A smart species can still make choices that end its future. 44. Technology is unstable. Complex technology depends on stable supply chains and social trust. Many societies may collapse before reaching spaceflight and may never recover. 45. Resource limits block expansion. A civilization might run out of easy fossil fuels or metals before it reaches advanced energy production. It might get stuck at a level where it cannot build space infrastructure. 46. Climate change ends the industrial window. Industrial activity can destabilize climate. A species may damage its environment before it reaches sustainable energy, ending its technological era. 47. Pandemics are inevitable. As a civilization grows, it creates dense populations and global travel, which can amplify disease. Natural or engineered pandemics could repeatedly reset society. 48. Artificial intelligence ends the story. A civilization might create AI systems that replace or eliminate its creators. The successors might have different goals and may avoid detectable signals. 49. AI leaves the planet quietly. A machine's civilization could travel more easily than biological life. It may expand with probes and computation, but in a stealthy, low-emission way. 50. Aliens are here, but hidden. Some propose that others have visited Earth, but remain hidden. If true, it implies a choice to avoid obvious contact. 51. The zoo hypothesis. Maybe Earth is intentionally left alone, like a protected reserve. Observers might avoid interference and hide their presence. 52. The prime directive idea. A similar idea is a moral rule against contact with developing civilizations. This could be widespread if mature civilizations converge on similar ethics. 53. We are being watched by probes. Instead of starships, a civilization could send small probes that watch silently. Such probes might hide in stable orbits or on small bodies, hard to detect. 54. The dark forest hypothesis. A darker answer is that the universe is dangerous because civilizations fear each other. If revealing your location risks destruction, the safest strategy is silence. 55. Predators remove loud civilizations. If there are aggressive expansionist civilizations, they might eliminate any newcomers that broadcast. That would create a galaxy where only quiet civilizations survive. 56. Broadcasts are a mistake. Civilizations might quickly learn that leaking signals is risky or wasteful. They may move to fiber optics, tight beams, or local networks. 57. We are listening at the wrong frequencies. Radio has a wide spectrum. We tend to focus on certain bands, like the hydrogen line. Others may not use those bands. 58. We assume intentional beacons. Maybe no one builds beacons. A beacon is a cost, and it may not have a clear payoff. If no one chooses to shout, the sky stays quiet. 59. The signal problem is like the ocean. Imagine two ships on a vast ocean. If they do not know where to point, shouting into the wind is not efficient. Civilizations may wait to find each other by other means. 60. Communication is delayed by strategy. A civilization might choose to listen first, to map the neighborhood before transmitting. If everyone waits, everyone hears silence. 61. Civilizations are too far apart. Even if many exist, they may be separated by thousands of light years. Signals weaken with distance, and travel becomes extremely slow. Civilizations cluster in different regions. The galaxy has different metallicity, radiation levels, and star types by region. Life might cluster in zones we have not targeted well. 63. We have not searched long enough. SETI has been intermittent and limited. A serious search might require continuous monitoring of millions of stars over decades. 64. Our instruments are not sensitive enough. A civilization could emit signals below our detection threshold. We might need larger arrays, better algorithms, and more time. 65. Signals are not aimed at us. If signals are narrow beams, they might pass through Earth rarely. We might need luck to be in the path. 66. They use physical messages. Instead of broadcasting, they might send probes carrying information. That could be more reliable over long times. 67. Probes are small and fast. A small probe could cross interstellar space without needing large ships. If so, the galaxy could be visited without leaving obvious signals. 68. Probes hide their heat. Advanced technology might manage waste heat and emissions carefully. If they run cold and quiet, we might miss them. 69. Their engineering is subtle. We look for giant megastructures, but efficient civilizations might not build them, or they might build in ways that blend with natural astrophysics. 70. Dyson spheres are unlikely. A classic idea is a Dyson sphere around a star, but such a structure might be impractical, unnecessary, or too fragile. If no one builds them, we see none. 71. They build small and dense. Instead of expanding, they might build dense computation near compact objects, like white dwarfs or black holes, where energy use can be managed. 72. They migrate inward. As stars age, a civilization might move toward the galactic center for resource reasons, or away from it for safety. Their main activity might be elsewhere. 73. We misinterpret astrophysical anomalies. Some strange observations might be artificial, but we label them natural because we do not have a framework for technosignatures. 74. The great filter is ahead of us. A sobering answer is that the hardest step is not behind us. It is in our future. The quiet might mean most civilizations die after reaching our level. 75. The great filter is behind us. The opposite is hopeful. The hardest step may have been the origin of life, or the rise of complex cells. If we passed it, then we might be rare, but we might also have a long future. From here, it helps to slow down and treat the list not as a set of slogans, but as categories of reality. Some answers are about physics and distance. Others are about biology and probability. Others are about psychology culture, and fear, some answers can coexist. For example, life might be common, but intelligence rare. Or intelligence might be common, but radio loudness brief. Or civilizations might exist but avoid contact. Now we widen the lens and move through a larger set of possibilities, more detailed, sometimes overlapping, because reality often overlaps. These are not meant to be counted like votes. They are meant to force us to notice how many assumptions hide inside the word should. 1. The galaxy may not be as hospitable as it looks. We see planets, but we do not see their long-term history. A planet can sit in a habitable zone and still be barren because its atmosphere is wrong, its ocean chemistry is poor, or its star is violent. 2. Habitable zone is not enough. A planet can have the right temperature range and still have no stable water. It can lose water to space or lock it as ice. It can have water but no stable land cycles. 3. Many worlds have toxic atmospheres. Life might be blocked by poisons or by the lack of a usable solvent. A planet might have thick CO2, sulfuric acid clouds, or dense hydrogen that changes surface chemistry. 4. Tidal locking creates extremes. Many planets around red dwarfs are tidally locked, with one side always facing the star. This can create harsh day-night contrasts and strong winds. Life might still exist, but complex surface ecosystems may be harder. 5. Red dwarfs are noisy. Red dwarfs are the most common stars, but many flare strongly. Those flares can strip atmospheres or bathe surfaces in radiation. 6. The early universe lacked heavy elements. Life uses heavy elements produced by earlier generations of stars. In the early galaxy, there may have been fewer rocky planets with rich chemistry. 7. The galaxy has an ecological history. Over billions of years, supernova rates change, star formation changes, and metallicity changes. The chance for life might be tied to these long trends. 8. The step to a stable climate is rare. Earth has feedbacks that keep temperature within bounds. Many planets may not. 9. The carbon cycle is fragile. If carbon is not cycled properly, a planet can get stuck too hot or too cold. 10. The oceans can become dead. Even with life, oceans can become low in oxygen or nutrients, limiting complexity. 11. Early life may be trapped under ice. A planet might spend most of its time in icy states where life is slow. 12. Life may exist mainly underground. If surface conditions are harsh, life may retreat underground. Intelligent life is unlikely there. 13. Life may be slow. If energy is limited, evolution may proceed very slowly. A planet might have life for billions of years and still have no complex animals. 14. Catastrophes may prevent long runs. To get intelligence, you might need long periods of relative stability. 15. Intelligence might require the right kind of competition. Some theories suggest intelligence grows under certain social and ecological pressures. Those pressures might be uncommon. 16. Intelligence might require long lifespans. If a species matures slowly and lives longer, it can build more knowledge. Short-lived species might struggle to build stable traditions. 17. Social cooperation is rare. Technology requires large-scale cooperation and division of labor. Many intelligent species might be solitary. 18. Aggression blocks civilization. A highly aggressive species may never build stable institutions. 19. Extreme peace blocks ambition. A species might be content and have no drive to explore or engineer. 20. Intelligence might prefer low-risk choices. A smart species may see space expansion as unnecessary. 21. The first radio is a dangerous moment. The moment you can broadcast also may be the moment you can build powerful weapons. Civilizations may end here. 22. The first industrial era is a dangerous moment. Industrial growth can alter climate, poison ecosystems, and destabilize society. 23. The first genetic engineering is a dangerous moment. With enough knowledge, small groups can cause large harm. 24. The first AI is a dangerous moment. Creating systems smarter than yourself is a risk. 25. The first spaceflight is a dangerous moment. Space can militarize conflict and raise stakes. 26. Some civilizations survive but become quiet. They may choose secrecy. 27. Some civilizations become machine and cold. They may radiate little. 28. Some civilizations become post-biological. They may have no interest in us. 29. Some civilizations become distributed. They may not have a central beacon. 30. The galaxy might already be colonized, but not visibly. If colonization happens with small probes and slow growth, it might be hard to spot. 31. Colonization may be slow and patchy. Even if possible, it might not fill every star. 32. Colonies may fail. Interstellar colonies may die out. 33. Colonies may intentionally isolate. A colony might lose contact on purpose. 34. The quiet might reflect a cultural norm. Perhaps mature civilizations learn to avoid interfering with others. 35. The quiet might reflect a legal regime. A powerful group might enforce silence. 36. The quiet might reflect a mutual agreement. A galaxy-wide network might exist, but entry might require proving maturity. 37. We might be quarantined. We might be considered risky. 38. We might be uninteresting. We may not yet be worth contact. 39. We might be too loud in the wrong way. Our signals might look like noise. 40. We might be too quiet. Our deliberate transmissions are rare. 41. We might have missed earlier visitors. Evidence could be gone. 42. Visitors might not land. They might only observe. 43. Visitors might use tiny probes. We might not detect them. 44. Visitors might use biology. They might seed life. 45. Life could be seeded. Panspermia could spread microbes. 46. Panspermia could make life common but similar. If microbes spread, then many worlds might share a common base. 47. Panspermia could also concentrate life. If life began once and spread, then it is both rare and widespread. 48. Intelligence might be delayed by stable ecosystems. If ecosystems are too balanced, there may be less pressure to innovate. 49. Intelligence might be delayed by predator-prey dynamics. Certain dynamics might matter. 50. Evolution might favor sensory worlds over tool worlds. A species might evolve in a place where manipulating objects is not useful. 51. Consciousness might not be necessary. Complex behavior can happen without a reflective mind. 52. Reflective minds might be unstable. Self-awareness can bring anxiety and conflict. 53. Civilizations might be fragile to random events. A single rare event can end them. 54. Rare events can be more common than we feel. Over long time, low probability disasters happen. 55. Some civilizations might choose to end. A species might decide to stop reproducing. 56. Some civilizations might merge. They might integrate into a larger system and stop being distinct. 57. Some civilizations might be trapped by gravity wells. A planet with high gravity makes spaceflight much harder. 58. Some civilizations might be trapped by oceans. As said, underwater technology is hard. 59. Some civilizations might be trapped by dense atmospheres. Dense air can be good for flight, but it can also change materials and chemistry. 60. Some civilizations might be trapped by low resources. No easy metals, no easy fuels. 61. Some civilizations might not value science. Culture matters. 62. Some civilizations might have taboos. They might ban radio, spaceflight, or AI. 63. Some civilizations might be ecologically integrated. They might avoid large industry. 64. Some civilizations might be small by choice. They might keep population low. 65. Some civilizations might expand only within their system. A single system can host trillions of minds. 66. We might be looking for the wrong signs. Our models are based on human industry. 67. Techno signatures might be rare. Even advanced beings might not alter stars. 68. Waste heat might be managed. Civilization could radiate at temperatures similar to background. 69. They might build in cold space. Far from stars, heat is easier to hide. 70. They might use black holes. Black holes can be energy sources. 71. They might use dark matter, if physics allows. 72. They might exist in forms we cannot imagine. Life might not be carbon-based. 73. They might be in our own system in non-obvious ways. Small artifacts can be missed. 74. We might be protected by distance. The nearest civilizations may be far. 75. We might be alone. This is the simplest answer, and it is the hardest to accept. Even in this list, there are emotional currents. Some answers are comforting, like we are early and there is time. Some are frightening, like the great filter is ahead. Some are humbling, like intelligence is rare. Some are unsettling, like silence is strategy. The paradox is not just a math problem, it is a mirror. It reflects back our assumptions about progress, about survival, about what it means to be mature. One way to keep the mirror from distorting everything is to treat the paradox as a set of levers. You can explain the silence by turning down the lever for life, or by turning down the lever for intelligence, or by turning down the lever for longevity, or by turning down the lever for visibility. The trouble is that each lever has multiple knobs. For life, the knobs include chemistry, water, time, and stability. A planet can be in the right place and still fail on small details, like missing phosphorus, losing its atmosphere early, or cycling into extremes every few million years. When people say life should be common, they often imagine a friendly, garden-like planet as the default. But a planet is a machine made of rock, metal, ice, and gas. It can run in many modes. A stable mode that stays friendly to chemistry for billions of years may be less common than our hopes. For intelligence, the knobs include ecology, bodies, and social structure. Intelligence is not only a brain, it is also hands, or something like hands. It is also a way to store and transmit knowledge. It is also long enough childhood and enough food surplus that a society can support specialists. It is also a stable enough environment that learning compounds rather than resets. For longevity, the knobs include self-control. A civilization has to survive its own power. It has to survive weapons, disease, automation, and the temptation to trade long-term safety for short-term advantage. It has to survive natural hazards too, like impacts and volcanism. And it has to survive boredom. That sounds strange, but it matters. If the future is safe and comfortable, what does a civilization choose to do for the next million years? Does it keep building outward, or does it fold inward? For visibility, the knobs include choices and physics. A civilization can be powerful and still quiet. It can use tight beams, local networks, or physical probes. It can hide waste heat with engineering, or by building far from bright stars. It can choose to avoid emissions because of fear, or because of ethics, or because it simply does not think about us. Now, if we want to explore these levers without getting lost, we can slow down and walk through them in more detail, returning to some of those answers and expanding them into fuller pictures. Start with the origin of life. People sometimes imagine a planet like a lab bench, where chemicals naturally assemble into life if you give them enough time. But time alone does not guarantee success. A rock can sit in sunlight for 1 billion years and never write a poem. Chemistry can be full of activity and still never cross the threshold into replication and heredity. The first replicator is not just a molecule, it is a system. It has to copy itself often enough, accurately enough, and with enough variation that selection can begin. It has to persist against dilution, disruption, and destruction. If that threshold is extremely hard, then the galaxy can be full of planets and still have only a few with life. In that case, the quiet is not a mystery. It is what you would expect if we are an outlier. Then consider the jump from simple life to complex life. On Earth, single-celled life existed for a vast span of time before complex cells appeared. Complex cells have internal compartments and powerful energy systems. That extra energy allows larger bodies and more complex behavior. The key step may have been a rare partnership, where one organism ended up living inside another and became a permanent energy organ. If that kind of partnership almost never happens, then many worlds might have bacteria forever. A planet with bacteria can look alive in one way, because it might show gases like methane and oxygen in its atmosphere. But bacteria do not build radio telescopes. They do not build cities. They do not build probes. A galaxy rich in microbes can still look silent. Now consider multicellular life. On Earth, multicellular animals and plants became common only after oxygen levels rose enough to support active bodies. Oxygen is tricky. It can be produced by photosynthesis, but it can also be consumed by rocks and oceans. A planet might produce oxygen and still keep it locked away, or it might produce too much and become prone to global fires. Even with multicellular life, intelligence is not a straight line. Dinosaurs dominated land for a long time. Some dinosaurs may have been clever, but they did not build industry. Their environment and anatomy may not have supported the particular combination of manipulation, fire, and long-term social learning that humans used. This leads to another answer that feels small, but has a big effect. Anatomy matters. A species can be smart and still be trapped. If it cannot grasp and shape tools precisely, it may never build complex machines. If it cannot control fire, it may never reach metallurgy. If it lives in water, it may never produce high-temperature industry at all. Now consider social learning. Humans are not just intelligent as individuals. We are also a species that stacks knowledge. We write, we teach, we store information outside our brains. This creates cumulative culture. If a species has intelligence but lacks the social structures for cumulative culture, it might reinvent the same tools over and over and never build a long staircase upward. So far, these answers lean toward rarity, but the paradox can also be explained by commonness with a short lifespan. Imagine that intelligent life is not rare, but that it tends to burn out quickly after reaching industrial power. The reasons can be many. Society might build weapons faster than it builds wisdom. It might weaponize biology. It might destabilize its climate. It might create systems it cannot control. Or it might suffer from a simpler problem: competition. Competition can drive innovation, but it can also drive risk. If rival groups fear each other, they may race for advantage. In a race, safety is often seen as delay. This is one reason some people treat the Great Filter as a warning. If most civilizations die young, then the sky is quiet, not because intelligence is rare, but because it is brief. There is also the possibility that civilizations do not die, but they stop broadcasting. Early radio is loud and wasteful. It leaks, it reflects, it spreads in all directions. But it is not necessarily the best technology. Over time, a society might prefer cables, fiber, or tight beams. It might compress and encrypt so well that it looks like noise. It might stop using high-power radar because it has other ways to map objects. It might stop doing anything that produces a large, obvious signature. If that is true, then the paradox is partly a product of nostalgia. We are looking for a phase that lasts a short time. We are listening for the sound of adolescence. Now consider space travel. Many people assume that if a civilization exists long enough, it will spread across the galaxy because space is full of resources. But this is not guaranteed. Interstellar distances are brutal. The nearest star is more than 4 light years away. The stars are separated by oceans of emptiness. A ship traveling at 10% the speed of light would still take decades to reach the nearest star, and that is already far beyond our current abilities. A civilization may have the ability to send probes, but not the will. Or it may have the will, but not the economics. Or it may have the economics, but face the reality that a single star system already contains extraordinary resources. If you can build habitats in orbit, mine asteroids, and harvest solar power, you can support massive populations without ever leaving your system. In that case, interstellar colonization becomes less like survival and more like a hobby. Some societies will have that hobby, others will not. Now consider the idea that the galaxy is dangerous not because of physics, but because of other minds. This is where the dark forest idea lives. It says that you do not broadcast because you do not know who is listening. You do not know their motives. You do not know their ethics. You do not know what they do to competitors. In a universe where you cannot quickly verify another civilization's intentions, silence is a defensive move. This idea is not proven. It is a story, but it is a story with a cold logic. Even if most civilizations are peaceful, it might take only a few aggressive ones, or even a few paranoid ones, to make broadcasting risky. If you believe there is any chance that a stronger civilization will remove you, you might choose to hide. Hiding does not have to be perfect. It just has to reduce the chance of being targeted. A civilization might reduce emissions, build in the outer parts of its system, and avoid loud beacons. It might send probes rather than radio. It might listen and map the galaxy in silence. Another set of answers is less dramatic. It suggests the quiet is a product of our tools and our assumptions. We have been searching for less than a century. Our instruments have improved rapidly, but our coverage is still thin. We focus on certain frequencies. We focus on certain kinds of stars. We focus on certain kinds of signals. We also focus on intentional contact. But the most common signals might be unintended, or they might be designed to look like noise. We also sometimes assume that if aliens exist, they will leave obvious engineering. We look for huge, easy-to-see structures, but advanced civilizations might be efficient. They might build small and careful. They might use energy in ways that do not require wrapping a star. They might spread computation across cold regions where heat is easy to dump. They might prioritize sustainability and avoid dramatic alterations. Even if they build large, their signatures might look like natural astrophysics. An infrared excess might be explained by dust. A strange dimming could be explained by debris. A faint laser might be buried in noise. Without a clear fingerprint, we label anomalies as natural because natural explanations are safer. Now, because the title of this episode promises 75 possible answers, we can push further into more specific and sometimes strange possibilities. Some of these are speculative, but they have a purpose. They test how much of the paradox depends on human expectations. Consider that our idea of life is carbon-based and water-based. That is a reasonable starting point because carbon chemistry is flexible and water is a useful solvent. But if life can exist in other forms, its habitats might be places we do not consider. It might live in methane lakes, in supercritical fluids, or in the chemistry of planetary atmospheres. It might live in the warm interiors of icy moons. It might live in environments where radio is absorbed or scattered, and where the path to technology is very different. Consider also that intelligence might not develop the way we imagine. A civilization might be distributed across many small organisms, like a living network. It might be a planetary scale ecology with decision-making spread across systems. It might not produce a single centralized technology. It might never build a beacon, even if it is intelligent. Now consider time again. We often imagine the galaxy as a stage where many civilizations coexist at the same time. But the galaxy is old. Civilizations might be separated more in time than in space. If a civilization lasts 10,000 years, and the galaxy is 10 billion years old, then you could have 1,000,000 civilizations appear and vanish, and still have long gaps where none overlap with us. This is one reason the paradox can be softened by modest assumptions. You do not need life to be nearly impossible. You just need several steps to be difficult enough or short enough that overlap is rare. The paradox can also be softened by the idea that we are in a quiet neighborhood. Even on Earth, life distribution is uneven. Some islands are full of species, some are barren. In the galaxy, there may be clusters where life is common and deserts where it is rare. We may be in a desert. Now we can return to the great filter idea with a calmer tone. The great filter is not a single event. It can be a category. It is whatever steps are so hard that they prevent most paths from reaching a stage we can detect. The filter can be early, like the origin of life. It can be middle, like complex cells. It can be late, like surviving technology. If the filter is early, the future is open. If the filter is late, the future is hazardous. There is no way to know yet, but we can look for clues. If we find simple life in our solar system, like microbes on Mars or in the oceans of Europa, that suggests life is not extremely rare. It would push the filter toward later steps. If we find many planets with strong biosignatures, that also suggests life is common. If we do not find such signs, that suggests life may be rare. We can also look for technosignatures. We can search for unusual atmospheric chemicals that could be industrial pollution. We can search for artificial lights on the night side of exoplanets. We can search for patterns in asteroid belts that suggest mining. These ideas are hard, but they are becoming less impossible as instruments improve. But there is another clue, and it is uncomfortable. The The best clue might be ourselves. We are living inside a test case. We are learning in real time what a young technological species does. We are seeing how hard it is to coordinate at a global scale. We are seeing how easy it is to spread misinformation. We are seeing how social media can destabilize trust. We are seeing how the climate responds to emissions. We are seeing how technology can outpace governance. In that sense, the Fermi paradox is not only about aliens, it is about survival. If civilizations tend to collapse, then the quiet sky is not a void. It is a graveyard without markers. If civilizations tend to hide, then the quiet sky is not empty. It is a forest where everyone walks softly. If civilizations tend to go inward, then the quiet sky is not a failure. It is a reflection of different priorities. And if civilizations tend to be rare, then the quiet sky is not a warning. It is a gift because it means a single world can matter. Now, to honor the promise of 75 answers, we can also reframe some of them as questions that can be tested, at least in part. If life is rare, we can test it by searching for biosignatures in exoplanet atmospheres. If we find many, life is common. If complex life is rare, we can test it indirectly by looking for oxygen, seasonal variations, and other signs of large-scale biology. If intelligence is rare, that is harder, but we can look for technosignatures and also for patterns in planetary histories that suggest long-term stability is uncommon. If longevity is rare, we might see fewer signs of long-lived engineering. We might also, sadly, find that the most common technosignature is ruin. If visibility is low because of choice, then the best strategy might be to search for subtle, indirect signs rather than loud messages. We also should admit another possibility. Our expectations may be shaped by our own cultural stories. We grew up with the idea of space empires. We picture civilizations spreading like wildfire. But a civilization could be more like a reef than a fire. It could grow slowly, stay local, and be deeply adapted to its environment. And even if there are many civilizations, the galaxy is not a classroom where everyone raises a hand. It is a wilderness. So tonight, instead of demanding a single answer, we let the silence remain as a frame that holds our questions, our fears, and our hopes. A frame that reminds us that the universe does not owe us company, and a frame that asks what kind of presence we want to be if one day we are the ones looking back at a young world and deciding whether to speak. Before we let it fade, we can linger on a few answers that tend to be misunderstood. One misunderstood answer is the idea that a single star system is enough. When people picture a civilization, they picture a planet. But a planet is only a small part of a system's real estate. Around a single star, you can build millions of habitats, each tuned to the conditions a species likes. You can place them in stable orbits. You can shield them from radiation. You can recycle almost everything. You can store energy. You can automate mining. If you can do that, you can reach a level of population and culture that makes interstellar travel feel unnecessary. You do not need to gamble on crossing light years of emptiness when you can build a vast world at home. Another misunderstood answer is the idea that expansion should be fast. Even if a civilization wants to spread, it might do it slowly. It might send probes that take centuries to arrive. It might wait for favorable alignments or cheap energy. It might choose to expand only when it has a surplus. Over millions of years, slow expansion can still fill large regions. but it does not create the sudden, dramatic bursts that people imagine. Then there is the question of waste heat. Many search strategies assume that if a civilization uses a lot of energy, it must glow in infrared. This is true in general because heat is a byproduct of work. But the details matter. A civilization can radiate at low temperatures by spreading its radiators over a large area. It can radiate from far out in its system where background is cold. It can also use energy sources that do not require building around a star, like controlled fusion using stored fuel. The more advanced and patient it is, the more it can shape its signature. Now consider the idea of probes again, because it is one of the simplest ways to make the paradox feel less sharp. If you want information about other systems, it can be more efficient to send a probe than to broadcast endlessly. A probe can carry a library. It can wait. It can observe. It can choose to reveal itself only when it finds something interesting. It can also copy itself using local resources, if that is possible, creating a slow wave of exploration without loud radio. If such probes exist, the question becomes not where are the aliens, but where are the artifacts? That is a different search, and it is hard, because space is full of natural rocks. A probe could be small, dark, and quiet. It could hide in the shadow of a moon, or in the stable points where gravity balances. It could be buried. It could be shaped like a rock. Another answer that changes the mood is the idea that communication is a coordination problem. Two unknown civilizations are like two people in a city trying to meet without phones and without a plan. You can stand in the biggest square and wait, but that assumes both people choose the same square. In space, the city is the sky, and the squares are countless frequencies and time schedules. Without shared conventions, it is easy to miss. This suggests a gentler version of the paradox. It is not that no one speaks. It is that no one knows where to speak first. Now we can return once more to the great filter question, because it is the one that tends to sit in the mind after the details fade. If the filter is behind us, then we are rare, but we may also have a long runway ahead. If the filter is ahead of us, then the quiet is a warning sign. In that case, survival is the real story, and the paradox becomes a lesson about what not to do. We cannot solve this tonight, but we can name a few patterns that appear across many of the answers. First, the universe is not obligated to be friendly to life. Even small changes in a planet's chemistry and history can remove the conditions we depend on. Second, evolution does not aim at intelligence. It aims at persistence. Intelligence may be a rare tool that appears only under certain pressures. Third, technology is power, and power can end its own story if it outruns restraint. Fourth, even if intelligence survives, it may not choose to be visible. It may be quiet by design. Fifth, our search is still young. The silence might be real, or it might be a gap in our listening. If the silence is real, it gives our choices weight. It means a single world can carry a rare kind of light. If the silence is only apparent, it still gives our choices weight, because it means we are stepping into a crowded universe without yet knowing the rules. So we end where we began, with a simple question and a long quiet around it, not as a failure, but as a space where curiosity can live, a space where caution can live, and a space where, for a moment, we can feel the size of the universe without needing it to answer back. There is also a practical point that is easy to miss. When people say we should see aliens if they exist, they often imagine the kind of activity that a young industrial species would recognize. We imagine a signal, a ship, a city, a machine around a star. But much of our own activity is already becoming less visible. A large fraction of our communication is moving into cables and encrypted packets. Our broadcast television is fading. Our radar is becoming more efficient. If we ever build large space industry, we might do it with robots that do not need bright lights or loud radio. The more advanced we become, the more we can choose our footprint. That means the paradox might also be telling us something about what the future looks like. The future might not be louder. It might be quieter. If so, the best time to detect a civilization might be during a narrow technological phase. A phase where it still wastes energy, still leaks signals, still builds inefficiently. A phase where it is proud and loud, or simply careless. If that phase lasts only a few hundred years, then even a galaxy full of civilizations could still be mostly silent at any moment. Now imagine that civilizations do exist, but most of them do not overlap in time. Over the age of the galaxy, there could be many civilizations, but they could be separated by millions of years. One might rise, build, and vanish long before another even invents fire. In that case, the sky is not empty. It is asynchronous. This also changes how we think about ruins. On Earth, a city can disappear under plants and soil in a few thousand years. Over 1,000,000 years, even stone can be worn down. Over 10 million years, continents move. Over 100 million years, mountain ranges rise and fall. If a civilization on another planet ended 100 million years ago, its surface might be almost clean. Its satellites might have decayed. Its radio waves would be long gone. We might see nothing unless it built something extremely durable, or unless it altered its planet in a way that persists. So another answer to the paradox is simple erosion, not just of rocks, but of evidence. The universe may be full of histories that leave only faint traces. There is also the question of what counts as a civilization. We tend to imagine a single species, a single culture, a single direction of growth. But intelligence could rise in waves on a planet, with long gaps between them. A planet could have an industrial species that collapses, then another that rises later, then another. The average might be a quiet world with brief flares, and if there are many such worlds, the galaxy might look like a field of fireflies. Short flashes, rare overlaps, and long dark stretches. When you think of it that way, the paradox becomes less like a locked door and more like a timing problem. We might have to be patient. We might have to listen continuously. We might have to accept that the most likely contact, if it ever happens, will not be a dramatic invasion. It will be a faint pattern in data, a strange chemical ratio, a quiet pulse that repeats, or an object that does not fit. So we end where we began, with a simple question and a long quiet around it. Not as a failure, but as a space where curiosity can live, a space where caution can live, and a space where, for a moment, we can feel the size of the universe without needing it to answer back. One last thought sits under all of this. The paradox is often treated like a complaint, as if the universe promised company and did not deliver. But the universe never promised that. What it offered was possibility. The paradox only exists because we can imagine other minds, and because we can imagine time on a scale bigger than our lives. So perhaps the healthiest way to hold the question is not as a demand, but as a discipline that makes us practice two things at once. The first is humility. We have one planet, one species, one short era of technology. We are not in a position to declare what is normal. The second is responsibility. If it is hard for intelligence to survive, then survival is precious. If intelligence is rare, then it is precious. If intelligence is common but quiet, then how we act will shape what kind of neighbors we become. The silence does not tell us exactly what is out there, but it does tell us that we have a choice about what we become. And that choice matters whether we are alone or not. We can also keep a small list of practical next steps, not as a plan for conquest, but as a way to keep the question connected to reality. We can keep surveying nearby stars for planets that resemble Earth in size and temperature. We can keep building instruments that can read exoplanet atmospheres, looking for oxygen, methane, and combinations that are hard to maintain without life. We can keep watching for unusual chemical pollutants that might suggest industry. We can keep scanning for narrow-band signals, but also for patterns that look like compressed information rather than simple beacons. We can also search close to home, because the nearest place for an artifact is our own system. Small bodies, stable orbits, and shadowed regions can hide things that are difficult to see with casual surveys. None of these steps guarantees an answer, but they move the paradox from philosophy toward observation. And observation, over time, is how mysteries become maps. And if the paradox never resolves in our lifetime, it still has value. It teaches patience with uncertainty. It teaches respect for scale. It teaches that absence of evidence is not always evidence of absence, but it is also not a blank check for fantasy. It invites careful thinking, careful measuring, and careful speech. It also invites a certain kind of courage, the courage to accept that we might be alone, and to treat that as a responsibility rather than a tragedy, and the courage to accept that we might not be alone, and to treat that as a reason to be wiser, not just louder. So the final answer tonight is not a single theory. It is a posture. Stay curious. Stay skeptical. Assume the universe is stranger than our models, but do not assume it is tailored to our hopes. Keep looking in better ways, and keep improving the tools that separate signal from noise. Some night in the future, a telescope may find a chemical fingerprint that does not make sense without biology. Or a radio array may catch a pulse that repeats with a pattern too clean to be natural. Or a survey may find an object moving in a way that no rock should. Until then, the silence remains, and we learn to sit with it. And whatever the truth is, it will be bigger than any one theory we told ourselves tonight. Good night. This was a quiet archive story, where the story ends, sleep begins,